This is the interim presentation for Team 4, Analysis and Redesign of a Mechanical Juicer. Product description. A mechanical juicer is a device designed to extract juice from fruits using only manual force. The user operates a lever system that applies pressure to the fruit, efficiently separating the juice from the pulp and seeds. The user provides a simple, durable, and sustainable alternative to electric models. Primary and secondary customers. The primary customers for the mechanical juicer are homeowners seeking a reliable and efficient way to make fresh juice, attracted by its manual operation, easy cleaning, and simple use. The secondary customers are restaurants and cafes that require a versatile juicer capable of handling different fruits and vegetables in larger volumes, making a modular design with interchangeable parts the most suitable option for their needs. Annual estimated demand is of 2 million units. However, our estimated production volume will be of 200,000 units.
Here we can additionally see the exploded view with labels on each of our components numbered 1 to 16. We additionally have a video displaying a potential assembly from that exploded view.
The fast breakdown for the mechanical juicer is the following. The core function is to extract juice. Key functional requirements are press fruit, meaning it must hold fruit and apply force. Filter juice, meaning it must contain waste and drop juice. It also has to be dependable. Therefore, the stability is going to be ensured. It must be convenient for the owner, and it must do this by multiplying the force and facilitating cleaning. It must offer potential enhancements to the product. And finally, it must please the senses of the owner by enhancing aesthetics.
To analyze the assembly sequence, we use two fishbone analyses. The first uses a bottom-up assembly with very limited sub-assemblies. First, we add the base and rubber feet, the bar and anchor, and then we add the holder and rubber cover, the funnel, the strainer, the bracket, the handle and the rubber handle, and the reciprocating pin and movable jaw. We connect the handle to the movable jaw using the link. The other method uses distinct sub-assemblies to increase parallel functions. We add the base and rubber feet, the bar and anchor, and then we use one assembly of the holder, the rubber cover, strainer, and funnel, and then we connect our last sub-assembly being the bracket, handle, rubber handle, reciprocating pin, movable jaw, and lid. We then analyze this based on ease of transferring and handling, ease of locating parts, ease of fastening joints, ease of testing sub-assemblies, and ease of assembling in parallel. Sequence 2, 1, all categories.
Here we have our function component mapping matrix, where we can see that most of the components have more than one function, and also that apply force and ensure stability are the functions most repeated.
Here we can see our bill of materials, which all of the parts. Material cost per part was estimated using recent industry costs for the raw materials and multiplying it by the mass of the part. Assembly time per part was then calculated using ME452 lecture and handling code, handling time per part, insertion code, insertion time. Assembly cost per part was calculated using that as a product of assembly time per part and the labor rate, which was assumed to be a rough average, US average of $20. Tooling cost was estimated based on rough part size and expected volume divided by total volume to find the total cost per part. All the assembly costs were combined for each part and summated to find the total cost of $67.12 to manufacture. Our product is less expensive to manufacture than similar products retail for, indicating reasonable numbers with a strong profit margin.
This is our quad chart, which compares functional importance and manufacturing cost, where we consider a high manufacturing cost to be above $4 per part. Based on the analysis, it would be ideal to eliminate the bar and interesting to resign the anchor, while most likely keeping the other parts unchanged. Next, we will discuss the product family design. After reviewing the functions in the fast diagram and considering both our primary and secondary customer groups, we determined that only one function needs to differ: hold fruit. This is because our secondary customer group requires different holders for different fruits, so that variation in function is necessary. The unique modules associated with these functions are the holder, the strainer, and the movable jaw. The base will also vary between customer groups to adapt the mechanical user to specific needs.
Our team's first modular interface is the press head module involving the strainer, holder, funnel, and movable jaw. For the homeowner variant, the press head has a larger diameter, which allows for a wide variety of fruits and vegetables to be used. For the restaurant variant, the press head is more specialized. This specific variant is designed for limes and kiwis and other small fruits and vegetables. Our team's second modular interface is at the base plate. For home applications, users will need a lesser capacity, while restaurant uses a larger capacity bowl. The raised bowl lip here also acts to serve as a location for the container used and to collect leaks as well. Assembly sequence, variant parts are installed at the start and mid-build. This results in extra handling and a longer assembling time. In the modify sequence, we build the common platform first. For this part, we have a few separate assemblies that prioritizes building of common parts. Only at the end do we snap in the variant-specific modules. As a result, time, cost, and complexity of the assemblies is reduced.
Thank you for listening.